You recently learned about Boolean expressions, and in these Boolean expressions, they evaluate to true or false. You can use these results inside conditional statements, so an if statement, an if else statement, an if else if, etc. Today we're going to learn how we can use combine Boolean expressions into a compound expression, and how we can also compare objects. So first, let's see what we did last time. Last time we talked about nested if statements, right? So let's say I wanted to do something for positive odd numbers. Well, I would want to either first identify my positive numbers or my odd numbers to kind of narrow the scope, right? So let's say, how do I find an odd number? Well, when we divide by 2, an odd number is going to have a remainder of 1. And so we learned about the modulus operator. Remember this little percent looking symbol. And so if a number is odd, the remainder when dividing by 2 is not going to be equal to 0. It's going to equal 1. So I could say if x mod 2 is not equal to 0, or I could say if x mod 2 is equal to 1, either way. Basically, if it passes that condition, we're talking about odd numbers. So now, how do I figure out which of those odd numbers are positive? Well, positive numbers are greater than 0. So if the number is greater than 0, so if it passes both of these conditions, if it's an odd number, and then if the odd number is greater than 0, we would do something. Now that's all well and good, but there is another way of combining this into something that's a little simpler, and that's through the use of logical operators. We have 3 logical operators. When you have 2 ampersands, like you do here, we call that AND. The AND logical operator will evaluate to true or false. It evaluates to true when both conditions are true. This one that looks like the parallel lines, this symbol means OR. Now if I have a compound statement using OR, that will evaluate to true when anything is true. So one of them, the other, or both can be true, and it will evaluate to true. This, we talked about last time, is not. It basically negates the current value. So if my value is true and I negate it, it becomes false. If my value is false and I could negate it, it's true. Now we can use truth tables. Now a truth table is basically going to lay out all the possible combinations for you. So for example, let's say I have 2 expressions, and I'm just going to represent those expressions by P and Q. What are all the possible combinations? Well, either both are true, both are false, and one is true and one is false. So these are my initial possible combinations of truth values for P and Q. And so now you'll notice when I do P and Q, I have to look at my P value and my Q value. And when both of them are true, it will evaluate to true. So that's why we have a true here. However, if either of them are false, or if both of them are false, it would evaluate to false. So for this, we need both to be true. For OR, we're just looking for any of them to be true. So true, true is going to be true. True, false is going to be true. False, true is going to evaluate to true. It's only when both of them are false that an OR statement will evaluate to here. So for AND, we need both. For OR, we need any. And then lastly, for our negation, I only need one variable. It's a unary operator. It's only applying to one thing. So if my initial condition is true, the negation is false. If my initial condition is false, the negation is true. So AND or not. So if you go back to that initial example with odd positive numbers, we wanted to have numbers that were both odd and positive. So instead of having 2 if statements, we can take our conditions and we can combine them into one longer condition joined by the symbol AND. So here was our first condition, here was our second condition. In order to do whatever statement is here, we needed it to pass both of these, for an and to be true, it must pass both of those. So those are logically equivalent. They evaluate to the same result every single time. So let's say we look at this example. So we have this Boolean, good age, that's going to be the result of age greater than or equal to 21 and age less than 29. Basically between 21 and 29, exclusive on the 29. You're considered a good height if you're between 78 and 84 units, whatever those are. And you'd be considered rich if your salary is more than 100,000. So, according to this, if you are a good age and a good height, or if you're just rich, we're going to print, okay, let's go out. Otherwise, we're going to say, it's not you, it's me. So how do I know what this evaluates to? Well, it really depends on the values for age, height, and salary. So let's say age is 23, height is 80, and salary is 20,000. All right, so we have to be a good age and a good height, or we have to be rich. So if I'm 23, am I greater than or equal to 21 and less than 29? The answer is yes. I'm greater than 21, I'm less than 29, passed. All right, what about height? If I'm 80, and that means I am greater than or equal to 78. I'm also less than 84, so both of those would be true, so it would pass this. And then salary 20,000 is not greater than that, so good age would be true, good height would be true, but rich would be false. So when I come to evaluate this, I would substitute my Boolean values, so good age is true, good height is true, and rich would be false. So let's see. Good age and good height. So remember, for an and, both of them have to be true, which is the case. So this would be true, and then this is false. But that's okay, because for an or, remember, any of them have to be true. And so this would say, okay, let's go out. But then let's say let's do another initial or another try and see what that comes out to be. Let's say I'm 20, 50 is my height, and my salary is still 20,000. All right, so here I'm a good age if I'm greater than 21 and less than 29. Right here, 20 greater than or equal to 21 fails. So because both conditions have to be true, I can stop right now. What happens is something called short circuit evaluation. When you have an and, if your first condition is false, it's not going to keep checking your second condition because it already knows the final answer. So this is going to be false. All right, what about good height? So height greater than or equal to 78. 50 is not greater than or equal to 78. So it fails that. And so just like before, it's going to do something called short circuit evaluation. It's not going to check the second condition because it already knows the answer because both have to be true. So that's going to be false. And then rich, salary greater than or equal to 100,000. 20,000 is not greater than that, so that fails. So if I'm a good age and a good height, or if I'm rich, well, I'm not a good age, I'm not a good height, so it fails this. But it's not going to short circuit evaluation because remember, with an or, it's just looking to see if something is true. And unfortunately it's not, so it's going to say it's not you, it's me. On the previous example, it did do a short circuit evaluation when this was true, and that passed. It didn't have to see if you were rich or not because you passed the first condition. Now realize that relational operators, your less than, your greater than, your less than or equal to, your greater than or equal to, it has a lower precedence than your math operators. So here you're going to evaluate 5 times 7, and you're going to simplify 3 plus 5 times quantity, 7 minus 1, before you compare them. So you always want to simplify your math expressions before deciding how they relate. Be careful though. This is a common error that students want to make. This does not translate to computer science, because what's going to happen is it's going to evaluate from left to right, and so it's going to compare 2 to x. So let's say x is 15. So 2 is less than or equal to x. That's true. But then how can you compare true to a numeric value? You really can't. And so you would end up with an error. If your goal is to say something like this in code, what you basically do is you separate it into 2 separate problems. Notice you have to repeat your variable, and you join it with an and. So if I want to say that x is between 2 and 10, I have to compare x against 2, and I have to compare x against 10. Now I'm not sure what happened to this chart, so let me go look at the one on the web really quick. All right, so we do have an order of operations that we follow in Java. Your negation, whether it's negating through your logical operator not, or it's like the negation of x, like negative x, those are going to have a higher precedence than everything else. And then our next level, now there's actually tons more levels, but for what we've learned so far, this is the order of precedence. Then you're going to do multiplication, division, or modulus in the order it appears. Then you're going to do addition or subtraction. Then you're going to do your relational operators. Then you're going to check equality or inequality. And then after you've done those, then would you do your anding or your oring. And lastly, if you have to assign to a variable, that's when you would assign, is the last thing you do. So you don't really have to memorize this. The more you get the hang of it, the easier it'll get, all right? So let's look here is just another chart. So with our logical operators that I'm talking about today, the negation is going to have the highest precedence. The exception is obviously if you force other operators through the use of parentheses, and then and or. So you might see a statement that looks like this, but what that is saying is here. So just like how last time I talked about be intentional with your use of braces when you're in your conditional statements, be intentional with your use of parentheses. So that way it is very clear your intention with the order. So in this expression, and has a higher precedence than or, so it's really equivalent to this. And then when you have an and followed by an and, you do the first grouping, and then that result gets grouped, and then you would do the or. And then here you would negate before you and then you would take that result and then do or. So just be very intentional with your parentheses and realize in the absence of parentheses, this is the order you will do your operations, not and or. So let's look at here. In this, you would get 2 different answers depending on if you evaluate and then or if you evaluate or and then and. If I do and first and then or, you'll get a true answer. If I do or first and then and, you'll get a false answer. So just like how doing multiplication before subtraction is important, same idea here. It's important that you do your and first and then your or. So the correct way to approach this would be I'd put my parentheses there to remember, and so I'm going to substitute 5 here, and I'm going to substitute 2 here and 4 here. Now 5 greater than 2 is true, When I'm ORing something, it's going to do something called short circuit evaluation because it doesn't really matter what this evaluates to. With an OR, as long as something is true, it evaluates to true. But we can see that how this would play out. So this will be false, which means the parentheses evaluates to false. But the correct answer is to evaluate and before OR. Obviously I didn't do the and, but the idea is still the same. I did this, and then I ORed it. So let's look here. In this, remember, we do our relational operators. And then we do our and. So y less than x. So 17 less than 42. That's true. Y less than or equal to z. 17 less than or equal to 25. That's also true. For an and, both conditions have to be true, which this is, so this will evaluate to true. All right, what about x mod 2 is equal to y mod 2, or x mod 2 is equal to z mod 2? So remember, I'm going to do this stuff and this stuff before I do OR. So x mod 2, 42 mod 2 is going to be 0, because there is no remainder when I divide by 2. 17 mod 2 is going to be 1. So 0 is equal to 1, that's false. Now let me come over here. X mod 2, 42 mod 2, that's going to be 0 because there is no remainder. And then 25 mod 2 is going to be 1. So 0 is equal to 1, that's a false statement. So with an OR, one of them has to be true. When neither of them are true, it's going to evaluate to false. All right, and this third one, x is less than or equal to y plus z, and remember this gets grouped together, this gets grouped together, we evaluate, and then we do and. So is 42 less than or equal to 17 plus 25? And the answer is true. Is 42 greater than or equal to 17 plus 25? And the answer is true. Because both of these are true, when I do an and, it's going to evaluate to true. What about when I have the negation? Well, first I have to figure out what's inside the parentheses, and then I can negate it. So here, x is less than y. Is 42 less than 17? And the answer is no. So straight away, I actually know the answer to the inside of my parentheses, and the reason is because of short circuit evaluation. It really doesn't matter if this is true or false. Because an and requires both to be true, and I already know this is false, I know my parentheses evaluate to false. And so when I negate that, that's going to evaluate to true. And then here, remember, I'm going to have to be careful with how I do this. I'm going to evaluate the stuff before my OR and the stuff after my OR, and then I'm going to compare it. So here, x plus y, so 42 plus 17 mod 2 is 0. Well, I know that's an odd number, and when I mod 2, I'm going to get 1 and not 0. So that's false. I'm not allowed to short circuit evaluate because in an OR, it's possible to still be true if my second condition is true. So let's look here. 25 minus 17, that's going to be 8. Mod 2 is 0. That's true, but wait, notice we have this exclamation point, the negation, and so this is going to be evaluated to false. So here, both things are false, so the answer will evaluate to false. So you need to take it in pieces. Now let's talk about something that will come up in coding bat. You might end up getting errors that say that you're not returning something. When you are expected to return a value, you must in every instance return an int in this case. So for example here, I'm returning either A or B. Right? If I'm trying to find the maximum number, I can compare this. If A is bigger than B, that's the maximum. Otherwise, I'll return B because that'll be the maximum. But you have to be careful because every path it takes must somehow get to a return value. One mistake students will make is something like here, if A is greater than B, return A. But let's say I do A greater than B, and that's true, I'm going to return A. What happens if it's false? What am I returning? The answer is we're not returning anything. So you're going to get an error because your computer thinks that you're not always returning an int. Okay, so let's say you decide to make a change. Okay, and you say to yourself, okay, well, let's check if A is greater than B. And if A is greater than B, we're going to return A. And if A is not greater than B, we're going to check to see if B is greater than or equal to A. Because in our brain, it makes sense, right? Either A is greater than B or B is greater than or equal to A. But remember, every time you test a condition, there's a true path and a false path. Even if in your brain, you're like, well, this encompasses all possibilities, logically to your computer, you had a true path and you have a false path, but what is being returned on your false path? And the answer is nothing. So even though mathematically these represent the entire universe possibilities, right? Your computer isn't thinking that way. It's thinking in terms of, okay, what is the flow? So here, true, I return something. False, I have a condition. When that condition is true, I return something. When it's false, I'm not returning anything. So even though in your brain you know you're always going to either be true here or here, your computer isn't recognizing that. So be careful. Don't ever end with a hanging else if. There are two ways of fixing that. So kind of like how we did before, you can say if A is greater than B, return A, otherwise return B. Or this is another way of doing it. When you have a return statement, as soon as you hit a return statement, you exit the method. So here I can test if A is bigger, and then if it's not bigger, I can assume to return B. So these are two different ways of doing the same thing. And the reason this is allowed is because when we hit a return, we exit the method and we don't continue with the code in the method. So let's say we wanted to write a method that accepts a pair of real numbers and returns the quadrant. So remember, in this quadrant, x and y are both positive. In this quadrant, x is negative, y is positive. In this quadrant, x and y are negative, and in this quadrant, x is positive and y is negative. So in quadrant 1, x and y are positive. In quadrant 2, x is negative, y is positive, etc. So here's one possible solution. This would be quadrant 1, when x and y are greater than 0. Notice you have to use and. In quadrant 2, x is negative, so x is less than 0, and y is positive. In quadrant 3, they're both negative, and in quadrant 4, x is positive, y is negative. And then if it's none of those, we're going to return 0 to mean that it's on an axis, because either x is 0 or y is 0. Now we have something called De Morgan's law that's kind of similar to the distributive property, and it's useful if you want the opposite of an existing test. So sometimes our things can get quite complicated, and you figure out one condition, but then you realize you want the opposite. What we can do is we can negate it. And so you'll notice here, if I negate an and statement, what I do is I essentially distribute my negation. I negate the first condition, so whatever that is, I negate it. I negate my and. Now the opposite of and is or, and then I would negate the second condition. Or I could do the same with an or. I would distribute my negation over here. I would distribute my negation over or, and that would make and here would make that. This is called De Morgan's law. So for example here, let's say I wrote this and I'm like, ooh, I actually wanted the opposite condition. So how do I find the opposite condition? Well, I can negate it. And so I would distribute this. Now the opposite of equal to is not equal to. The opposite of and is or. And the opposite of greater than, and here's where students make a mistake. They want to say less than, but it's actually less than or equal to. And so that's what I just did here. So in Java, if I wanted to negate this, again, I would distribute. I would distribute, and I would distribute. So right now in English, it's saying, okay, it's not true that age is smaller than 12 or greater than or equal to 65. That sounds kind of complicated, right? So I can simplify this by distributing over less than, negation is greater than or equal to. The negation of or is and the negation of greater than or equal to is less than. We can prove Boolean identities, Boolean rules, by using a truth table. So remember, in a truth table, you want to set out all the possible combinations. So when you have two expressions, there's going to be 4 possible combinations of initial truth, true and false. So either both start out as true, both start out as false, or one starts out as true and the other starts out as false. So you'll notice when I do a truth table for this, A and B, so true and true, would be true, and then I negate it, which is false. Here, A and B would be false, and then when I negate it, I get true. A and B, remember, both have to be true. So false and true, that would be false, and then when I negate it, I get true. A and B would be false. When I negate it, I get true. So here are the values of this. And then here you'll notice when I do this, if I negate A, and if I negate B and then I OR it, it would evaluate to false. If I negate A, and if I negate B and I OR it, it would evaluate to true. If I negate A and I negate B and I OR it, it would evaluate to true. And then here, if I negate and negate, it would evaluate to true. You'll notice here, both of those are false, both of those are true, both of those are true, and both of those are true. That means these expressions are logically equivalent. They produce the same truth values given the same initial condition values. So I've talked about short circuit evaluation, so just remember, and will stop early if the first part of the test is false, or will stop early if the first part of the test is true. Now, we've talked about objects before. You have to be careful. When we use double equals for primitive data, it's straightforward, it's easy, it's checking to see if they're the same. But when we are using it to compare objects, we're actually looking to see if objects are aliases of each other. So let's say, here's my house, and you ask me for my address, or you ask me for my son's address. Well, my address is talking about this house, and my son's address is talking about this house. And so if I'm comparing my to my son's, this would be true because we have the same address. So this is actually checking to see if two different variables are pointing to the same object, if their addresses are the same. Equals, on the other hand, is actually checking to see if the objects are the same. So let's say I have this object that has data, a character X, a number 1.3, and then I have another object that has X and 1.3. And here I have a variable that's pointing here, and I have another variable that's pointing here. Now, if you were to ask me if var1 is equal to var2, the answer is no, they're not pointing to the same object. But if you were to ask me if var1 equals var2, and I'm looking at these objects, the content looks the same, this would be true. So there's a subtle difference that makes more sense as we get more into objects, but just realize that when we're using double equals, it's looking to see if the address is the same. When we use dot equals, we're looking at the contents to see if they're the same. Now, strings act a little funny. Here, if I have a string literal hi, and I create a new string hi, these are pointing to different objects. Now you might say, but they both are hi. That's because the contents of them are the same. So dot equals would come out true. Now, in reality, just remember to use dot equals for strings, and then it becomes pretty easy. But here's a visualization of what's going on, right? Here, these two variables are pointing to the same thing. So S1 is equal to S2. Now, if S1 and S2 have the same address, then using dot equals would also evaluate to true. However, when we have a situation like this, when the contents are the same, but they're basically two different objects, S1 would not equal S2 using this relational operator. However, the contents would be, and then this would just be false. Now, in reality, there's a little bit more complex answer. If you use the shorthand way of creating a string, those strings may get put in something called the string pool, and so it may be true that S1 is equal to S2 if they're both pointing to the string pool, but when you use the longer version of new string, it's not going to go to the string pool, it's going to create a separate object. So there's a more complex answer. You don't really have to understand that. Just stick with dot equals, okay? And then you won't have to worry about it. All right, so if I wanted to look at strings and decide if it's a vowel, I would want to use dot equals to compare each of the combinations against my values. I wouldn't want to use double equals. All right, and so if I wanted to see if it wasn't a value, then I could take my answer and I can negate it. And remember, when I negate it means I distribute over each thing. So then I would say not equals to A, and etc. All right, so here's some sample labs if you want to do them. I know it was a longer video, but it had a lot of information in it. That's kind of important. All right, good luck.